Hello everyone. You had some lecture from 11 to 12. Ravya? Okay. Which subject? MQA. Okay. Who is teaching MQA? Puri sir? Shital madam? Prajwal? Kani sir. Okay. Well, all of you have the soft copy of design data book, right? Shravya?
Yes, ma'am.
Okay. Okay, I don't know what page numbers are matching or not. Open the design data book or refer to the page number 164 as per my data book. Table number 16.1. Table number 16.1, design formula for spur gears. Do you have the complete soft copy of the design data book, or these are the photographs or images from different pages? Atharva?
Ma'am.
Sorry?
Images. Like some person who had took the images and combined it.
Acha, okay. Can you search on this table number 16.1? Okay. So PDF page number is 86. What is the title of the table? What is the title given on the table? Design formula for spur gears. Okay. All of you on same page with me? Okay, so we'll go through the design data book quickly and then we'll solve the numerical based on this. The first formula is giving you the design power, which is rated power into a load factor. Now, load factor is given on a table on the next page, that is table 16.2. which is giving you the load factor depending upon the type of the load and the type of service. Whether it is steady load, light shock, medium shock, or heavy shock. Can you tell me what is the difference between light, medium, and heavy shocks? You understand the type of service, intermittent or 3 hours per day. So a particular machine component or gearbox is running only for 3 hours in a day, 8 to 10 hours per day, or it is continuously working 24 hours per day. When do you, or on what basis you select whether it is light shock, medium shock, or heavy shock? Rishabh?
I'm sorry, ma'am. Can you repeat?
Jewel, anyone from this group, do you know what is the difference between light shock, medium shock, and heavy shock?
No, I'm not sure.
Not sure, okay.
Something
So
like a
let me
jerk
tell
or
you
something.
about, yeah,
Something like a jerk to the when the gear is moving.
yes. And when do you get a jerk? In what kind of machines you would get a jerk? You have studied theory of machines to balancing? Yes,
Yes.
no? Yes.
Yes.
Okay. Which machines will have more jerk, rotary or reciprocatory machines?
Reciprocity.
Reciprocal. Because it cannot be completely balanced, whereas a rotary machine can be balanced.
Completely balanced.
Yeah. So a steady load is usually when there are no rotating parts or minimum number of rotating or reciprocating parts. That is a steady load. So normally for steady load for 8 to 10 hours per day, this is the most ideal situation where the load factor is 1 as it is given. If you have an input is usually say a motor, and then you have an output. Say a motor is driving a diesel engine or a generator, or it is driving a pump, or it is an automobile or an internal combustion engine which is input, and then output is some other application, say a compressor. So you have an input and you have an output, and in between you are coupling the shafts, and then there is a gearbox mounted to reduce the RPM or to increase the torque. So if the input and output both are rotary, this is rotary, this is also rotary, then it is light shock. If one of them is rotary and another is reciprocatory, so there are shocks here. So this is medium shock. And if both are reciprocating, a reciprocating IC engine is operating a reciprocating pump or a compressor, then this is heavy shock. Now, when you are designing a problem, it will never mention what are the input or the output machineries, whether it is light shock, medium shock, but it would probably specify it is an electric motor which is driving a drum, or which is driving a pump, or something would be mentioned. So based on what are the input and output, we design or we pick up what is the kind of shock, and accordingly we select what is the load factor. So what is the value of load factor for medium shock continuous duty, continuous service 24 hours per day? From the table, 1.8. This is the service factor, which means if your rated power is say 100 kilonewton, then we multiply it with 1.8, and we are designing it for 180 kilonewtons because it has medium shock. So that is the amount of jerk, and so our design load is increased. So we are designing a gear for 180 newtons. That is the meaning. Come back to table 16.1. The tooth load or the static load Ft is given as design power upon Vp, which is the pitch line velocity. You know this formula, where Vp is pi dn by 60. Then the Lewis equation is given, where Fb is the beam strength or the bending strength of the beam in bending. So you call it bending strength or beam strength, which is equal to S naught, where S naught is the strength of the material. Cv is the velocity factor, which we discussed in the other class. B is the face width, Y is the Lewis form factor, and M is the module. M is the module. Then the dynamic load Fd, this also we discussed. Fd is sum of Ft plus Fi, and the formula for Fi is given. This is the Buckingham's equation. C is the deformation factor, and the value of C deformation factor is given in table 16.4. You see that table? Depending upon what are the materials, whether it is steel and steel for both gear and pinion, or grey cast iron and steel, and the pressure angle that you are or the gear profile that you are selecting, 14.5, 20 or 20 degree stub tooth, you get the value of C. Suppose you select grey cast iron for both gear and pinion, and if you select 20 degree full depth, what is the value of C given in the table? 5900. That is the value of C given. So this is how we are going to refer to the design data book. So this gives you the value of C. E is the error. Now as per my data book, the next page, so if 164 is this table 16.1, page number 165 is giving me two graphs. Figure 16.1 is giving probable error in the spur gear, and 16.2 is giving permissible error in the spur gear. Which one would you select? This is giving you the value of E for given module. So the probable error is a graph between error and module, and permissible error is a graph between error and pitch line velocity. Which one would you select? Probable error or permissible error? Permissible. Why? What is probable and what is permissible?
Probable is after designing what is the possibility that how much error would be given, and permissible is to what maximum extent the design gear can be used. So
Exactly.
we'll be choosing permissible error.
Exactly. Okay. Now, if you know the class of the gear, whether it is commercially cut, carefully cut, or precision gear, as is given there in the table. So a commercially cut gear would have maximum error, whereas a precision gear will have minimum error for the same module, as you can see in the graph. And a carefully cut gear is a class 2 gear which lies between class 1 and class 3. And if your pitch line velocity is known, as the velocity increases, the permissible error goes down. As you can see, the graph is showing a hyperbola. Normally, if the class of gear is known, we'll go with the probable error. And whatever the probable error you are selecting, you have to ensure that this is less than permissible error, because permissible error is the maximum possible limit of the error. It should not exceed that. So we will go with probable error in our numericals. Value of C you know, E you know, Vp you know, B is the face width which we will get from module. Ft will calculate from the power and the velocity. Then the VS strength. VS strength we discussed the other class, where D is the pitch circle diameter. Fw, the wear strength is given as dP into B into K into Q, where K is the load stress factor. Q is the size factor which depends upon number of teeth on gear and pinion, whether it is external or internal gear. What do you understand by internal gears? Sania?
Yes, ma'am. So I think the the center of the one gear is inside the other, and the teeth is on both sides. So those could be internal gears.
Teeth is on both sides of what?
Yes, ma'am.
Teeth is on both sides. What does that mean?
Ma'am, I'm not sure about it.
Okay, no problem. Who else can give me this answer? Aditya?
I mean, ma'am, actually, the inner part of the outer gear will have teeth, and the outer part of the inner gear will have
Correct.
teeth.
So I know you know the answer, but you are unable to explain. Why so? So this is an internal gear with, say, teeth cut here, and this is a pinion which has teeth on the outer surface. So they are meshing like this. This is internal gear, and an external gear is when both the gears have teeth cut on their outer surface. This is external gear. So depending upon whether it is internal gear or external gear, we have different formulas for this size factor Q. And for load stress, there is another table for the value of K, which is the load stress factor, table 16.6, which is talking about what is the hardness of the material, what is the pressure angle, and accordingly we'll select what is the load stress factor. So it is the hardness of the material and the material itself which will decide how the wear strength would change. Whether the wearing would be quick or it would be slow, it would be delayed. You can also see for the same hardness in this table, suppose I select steel with BHN 500 for both gear and pinion. For 14.5 involute profile, what is the value of K? What is the value of K? 2.555. For both gear and pinion, hardness 500. Pranay, check it again, please. Yeah, it is 3.019, and for 20 degree. Pranay, for 20 degree, 4.123, which means as the value of K increases, the wear strength would increase. Agreed? Which also means that with 20 degree pressure angle, the wear strength would be better, which is what we discussed in the last class. And then we also check for endurance strength. And what is endurance? Saurabh, what do you mean by endurance? Saurabh?
Ma'am, max.
Yeah.
Yes.
Yeah.
Maximum limit before failure means maximum stress it can handle.
Maximum stress induced because of what kind of loading?
Dynamic loading, ma'am.
Dynamic loading or fluctuating loading. And so the endurance life will be normally mentioned in terms of cycles, 10,000 cycles, 20,000 cycles. So we'll also check for the endurance strength. Your gear tooth might be safe in bending, it might be safe in wear, but after given number of cycles, if it fails, then it is weak in the endurance strength. So we'll design this as well, where the endurance strength is given in the table 16.9. For the reverse bending and surface endurance, we'll be going with reverse bending. Value of B, Y, and M would remain the same. You got the table 16.9, which is giving you the endurance strength for reverse bending. Or phosphorus bronze with BHN 100. What is the value of endurance strength in megapascals? 168, right? Which means you have the soft copy of design data book. Good. 16668. Anybody value can't say any? Some typos error. Okay. Then again refer to table 16.7. which is giving you the standard modules available. There are two rows. One is giving the preferred choice of module and second is giving the second choice. We'll usually go with the preferred choice where the module is 1, 1.25, 1.52. These are the standard modules. Only for specific application where you don't want to shift from 1.25 to 2 directly or 1.5, there you can go for 1.375 likewise. For the compact design, where the pinion shaft diameter is given, then the pitch side diameter of pinion, depending upon whether it is keyed or it is integral. You know the difference between what is a keyed shaft and what is a gear integral with the shaft. Do you know this difference, Richa?
Ma'am, in the key, there is a slot in the shaft and the gear where a key is added to keep them in contact so that it doesn't have any action motion.
Perfect. What is an integral shaft or a pinion mounted integral with shaft?
And I think it is attached permanently to the shaft.
Yeah, so it is as if made in a single part. So it has a gear which has a projection on the either side which is acting like a shaft. So that is integral. So accordingly we select what is the pitch circle diameter of the pinion. Similarly, we can refer to the economical design. So either you go with the compact design or you go with the economical design. A compact design will make your gearbox very compact if you have space constraint, and if the cost is the constraint, then we go with the economical design. Go to the next point 4, which is giving the preferred number of teeth on pinions. So you can see a minimum number of teeth can be 7 to 9, but it should have long addendum so that there is no undercutting, 25-degree pressure angle, poor wear characteristics. So this is the number of teeth which we will never use unless it specifies that undercutting is allowed, poor wear is allowed, 25 degrees is allowed, which is rarely the case. We will always go with 25 number of teeth, which is a good balance in strength and wear. If you go with 50, then it has excellent wear resistance and for the quiet operation. And then the face width is given in terms of module, which we have discussed. So with this much information, there are two more tables which are giving you the formula for modified Lewis form factor Y and the velocity factor CV. So let's start solving the problem and then we'll come to this. One more point is, what would be the velocity ratio in case of spur gear? And to what extent you can reduce the speed of the gear from the pinion? Any idea? This again you have studied in theory of machines. I doubt whether you remember. What is the range of velocity ratio? Not more than 6. Perfect. So it should normally be in the range of 4 to 6. And if you want to go beyond 6, what do we do? What would you do if you want to have a velocity reduction? Yeah, perfect. Use a train, gear train, or we go with the helical gear. So in case of helical gear, we'll be having velocity reduction or velocity ratio as high as 10. Okay, so take down this problem. An electric hoist What is a hoist? Atharva? What is a hoist? Rajwal? Anyone? Anyone can tell me what is a hoist?
Ma'am, it's some
thing used to lift heavy things.
Perfect.
Like,
Perfect. So a crane is also a hoist which is used to lift heavy weights, or an elevator is also a hoist which is used to lift the entire cage. So electric hoist is being designed for a lifting capacity of 30 kilonewton. You please write down the complete problem statement. An electric hoist is being designed for a lifting capacity of 30 kilonewtons at a speed of 80 meter per minute. The diameter of the rope drum used to lift the weight is 600 mm. Which is driven by an electric motor at 1440 rpm. So there is a drum which has a wire rope. At the end of the wire rope there is a weight, and this is lifted by a motor which is running at 1440 rpm, and they are connected through spur gears. Spur gears is what we are designing now. Through spur gear. Suggest suitable number of stages. Suggest suitable number of stages for the reduction drive and design the gears for continuous duty. Continuous duty. So a rough sketch of this is the rope drum. This is the weight. It is able to lift 30 kilonewtons of weight, and through spur gears this is connected to a motor over here. This is an electric motor running at 1440 rpm. Can you give me the rpm of this rope drum whose linear velocity is 80 meters per minute and whose diameter is 600 mm? What is the rpm of the drum? I want quick answers. Please, all of you continue to calculate. Keep your calculators handy. If the linear speed is 80 meters per minute and if the diameter of the drum is 600 mm, what is its angular speed in rpm? Who is giving me the answer? This is the linear speed 1 pi into d of this drum, which is 600 mm. This is in meters, and so you will divide this by 1000. 42.4. Motor is running at 1440 rpm and drum is running at 42.44 rpm. So what is the total velocity ratio between the input shaft to the output shaft? What is the velocity ratio? (34). Is it 33.9? 34. This is the velocity ratio. What is the maximum limit for a spur gear? The velocity ratio can be a maximum of 6. So if we want 33.9, then we should have reduction in 2 stages. In the first stage, it reduces from 1440 RPM divided by 6, which is the maximum velocity ratio. So how much would be the RPM reduction after first stage? 240, and in the second stage we'll reduce it from 240 to 33.9. So here, what is the velocity ratio?
Ma'am, we
Yeah.
reduce it to 42.4.
Sorry, thought something is wrong. Thank you for the correction. 42.4. So this is velocity ratio is 5.6. So we are having 2-stage reduction. At the first stage, the velocity ratio is 6. Velocity ratio for first stage is 6, and the velocity ratio for second stage is 5.65, which means we can use per gear for both the stages. So here there is a pinion meshing with a gear where the velocity reduces by 6 times. So from 1440, this comes down to 240, and there is again another pinion and a gear. So this particular pinion is rotating at 1440 RPM. This gear is rotating at 240 RPM. Because these two are mounted on the same shaft, this is also rotating at 240 RPM. And then here the reduction is 5.65 times, and so this rotates at 42.4 RPM. And this gear is mounted, or this is on the same shaft in which this drum is mounted. So drum also rotates at 42.4 RPM, giving a linear speed of 80 meters per minute. So we have to design this gear pair and we have to design this gear pair. Till here, is that clear what we have done? Is this part clear? Atharva? Rishabh? Okay. Let us start with first gear pair. What start? I am going to tell you about the first gear pair. Second gear pair, I want you to design. Yes, please.
Ma'am, 6 is coming from limitation of velocity gear ratio.
Sorry, I didn't get you. What is your
Ma'am,
question?
why we are dividing by 6? 1440 by 6.
Okay, here the velocity ratio that maximum you can have for a spur gear is 6, which means you can reduce only from 1440 to 240. Because this is the maximum limit of velocity ratio that a spur gear can have.
Okay.
Isn't it? Which means for the first stage reduction is 6 and total reduction of velocity ratio is 33.9. And so for the second stage, the reduction is 5.65, so that you reduce from 240 to 42.4. Is that okay? Is that okay?
Yes, ma'am.
Okay, good. So now we are going to start with the design. Say this is pinion 1 gear, 1 pinion, 2 gear. Let us start with designing the first gear pair P1 G1. The first thing that we know is the design power. We have to get the design power PD. Now this entire design will take 1 hour time minimum, which in exam you are expected to complete in half an hour or 20 minutes. So if you practice more, you can probably do it. Rated power into the service factor K. What is the rated power? It has to lift a weight of 30 kilonewton with a linear velocity of 80 meters per minute, which means the rated power is 30 kilonewtons into 80 meters per minute. Convert it to seconds and you will get it in kilowatt. Give me this value. This is kilonewton into meter per second. This is the load it has to lift at this linear velocity. Do we get 40 kilowatt? This is the rated power. Now this is the power available or the power required at the drum. Do you think the same power will be generated at the motor with so many moving parts?
We will require more power.
More power, yes. To account for the losses, we will require more power here. So the rated power should be more if you want 40 kilowatt of power here. Normally, the efficiency of a gear drive is how much? What do you think? What is the efficiency of a gear drive? How much would it be? Any idea? About 95, yes. It is almost 98%, 97%. That is the efficiency of the gear drive. So the losses are minimum if the gears are perfectly designed. So let's take it 98% efficiency. So we are assuming efficiency of the gear or the gear pair as 98%. And so the rated power at the motor would be the rated power 40 kilonewton at the drum shaft upon 98%, that is 2% loss in P2G2 second gear pair into 2% loss in the first gear pair. You can go with 95% also, or if you don't want to take this, you can just write down assuming efficiency of the gear pair is 100%. And you can continue with 40 kilowatt. In a design problem, the answer doesn't matter. What really matters is whether you know that there would be a loss. So if you're assuming 100%, that means the losses are minimum. So what is the rated power of the motor?
1.68.
Yes. And now we'll see what is the design power. This is the rated power of the motor, and so what is the design power? PD. It is continuous duty. And what about the shock? What type of machines we are using at input and output? Rotary and reciprocatory. Motor is what? Motor is rotary. And the drum is what? Drum is also rotating. The load is traveling in a linear direction, but drum is also rotating. So it is light duty, 24 hours per day. Give me the value of K. Give me the value of K. 1.8 or 1.5? Light shock continuous operation, it is 1.5. 41.65 into 1.5 is how much? This comes out to be give me the answer.
$62.47.
Okay. You can as well continue with this. There can be one more assumption. Now this is the rated power 41.65. Normally the motors, electric motors that are available are for 40 kilowatt, 45 kilowatt, 50 kilowatt. So if we pick up a standard motor, then the standard motor, the next available standard motor will be available for a rated power of 45 kilowatts. So if I am selecting this motor, what are the standard ratings available for the motor is also given in the design data book. Selecting the motor of next available value, that is 45 kilowatt. So if I take this as PR, what is my PD? This rated power multiplied by the service factor. So this is how much? 67.5. Now we are going to design for this power. Now this is the power available at the pinion 1 and we are starting with the design of pinion. This is the design power of the motor and the motor is carrying the shaft which has the pinion 1. So we are starting with design of pinion 1. Pinion which is mounted on the motor shaft, where the power available is, or you have to design it for 67.5 kilowatt. So we'll always start from assuming the number of teeth on the pinion. How many number of teeth you will assume? We discussed just now 25. For good balance, we always go for 25. You can mention here for good balance. This will always keep you safe. Now module will always assume as M. We don't pick up a value. We assume the value as M. We'll solve everything in terms of M and then we get the value of M. So if module is M, what will be the diameter of the pinion or number of teeth T module M? What will be the diameter, pitch circle diameter of the pinion? Ambika, 25 M. That is 25 times module and this is in millimeters. So what will be its peripheral velocity or the pitch line velocity? RPM is 1440. Pitch circle diameter is 25 M. Give me the value of Vp. Pi d n upon 60. Give me the value in meter per second. .88 meter per second. 1.88 times m. This is now in meter per second. This is Vp. So what is the static force responsible for power transmission? This is the design power upon this peripheral velocity. You will get something upon m. Give me the value in newtons. Yeah, it is 35.9 upon m kilonewton. 35.9, 35.8, 35.9 upon m kilonewton, or this is 10 raised to 3 Newton. This is the force which is responsible for transmission of power. Next, we will select the material. Feel free to ask me questions, otherwise I'll continue to move ahead. If you have any doubts still here. Next step is material selection. Are you getting it, Vaishnavi? Sushmita?
Yes, ma'am.
No doubt still here?
No, ma'am, no doubt.
Good, good. Okay, now how do we select the material? Refer to table 1610. It gives you gear material and their strength. You found that table? Table 1610 for gear material and their strength. Cast
Yes,
iron
ma'am.
is given ordinary, medium grade, high grade. Cast steel is given untreated and heat treated. Then SAE grades for forged carbon steel, alloy steel is given. Normally, we'll be selecting the SAE grade. Normally, so there is no specific reason. But by and large, we'll be selecting this grade. So as we solve more problems, I'll tell you why normally we are in this range. So what do you want to select? SAE 1040, 1045. Should we go with SAE 1045? Heat treated, untreated, heat treated. Okay. So let us go with material as SAE 1045. Treated, untreated, which one you want me to select? Say untreated, okay. And we have to also select a material for gear. Now, normally the gear is rotating at a lower RPM than the pinion. Or a pinion is rotating at a higher RPM, as we have seen. Pinion is rotating at 1440 RPM and gear is rotating at 240 RPM. Pinion is smaller in size, rotating at a higher RPM. So out of gear and pinion, the material for the pinion should usually be stronger. Stronger in the sense its strength should be more. You can as well go with the same strength, but to economize, we can go for a gear with a lesser strength. So if you are selecting SAE 1045 for pinion, you can select SAE 1020 for gear or SAE 1035 for gear, which is little smaller than this. Okay. So which one you want to select? You can as well go for this cast steel also for gear. Let us go with cast steel. Yes.
Ma'am, why should pinion be stronger than gear? Because gear has more length on its teeth.
Yeah, but the RPM is less. It is rotating at a lower RPM. For the same power transmission, because RPM is less and it has to undergo lesser weight, and pinion is smaller in diameter, rotating at a high RPM, which means there's a chances of failure of pinion is high. We also have a test of which one is weaker and stronger. So that I'm coming to it once we select the material for the gear. So I'm coming to this point again. Suppose this SA1045 untreated is selected for pinion. And suppose I am selecting cast steel. As I said, you can go with SAE series also. Let me select cast steel 0.2% heat treated for gear. So what are the values for S0 for pinion and for gear? 210 for pinion and 196 for gear. Now, how do you decide whether we are designing for gear or pinion? For this, there is a test S0 into Y. Y is the lowest form factor for gear is compared with S0 into Y for pinion. Now Y is the lowest form factor which depends upon geometry and number of teeth. Now whichever is lesser of two, out of these two, whichever is lesser, that becomes weaker. And if that is weaker, we design for the weaker of the two, whether it's gear or pinion. So we have already selected the gear material whose S0 is 196 as against pinion whose S0 is 210. Okay. Number of teeth on pinion. Number of teeth on pinion 25. Number of teeth on gear. With velocity ratio 6, what will be the number of teeth on gear? 150. And give me the value of Y. Now this Y depends upon number of teeth. Have we selected the profile? Table number 16.5 is giving us the value for modified lowest form factor. So normally what gear profile will be selecting? Shravya?
Ma'am, 20 degrees full depth.
Full depth, okay. So the formula for Y is given as how much?
0.485 minus 2.87 by T.
Right. So give me the value of Y for pinion and gear. And I'm coming to your in this design data book, SAE untreated and heat treated, this here is talking only about its basic strength. It is not talking about its hardness or ductility or the stress relieving part. So that is required for checking or for taking into account the other factors. We are here talking only about the strength. So advantage of going for untreated material or heat treated material, this is not obvious from here. And the last one G, which is written SAE 1045 heat treated, that is actually SAE 1050. It's a soft copy, you cannot edit it, but keep in mind the last one, the G is SAE 1050 heat treated 245. Have I answered your question? Number 23, what's your name? Okay, so YP is coming out to be 0.37 and 0.46. Abhi, tell me what is S0 into Y for gear and S0 into Y for pinion and which one is larger? So what is S0 into Y for pinion? For gear. Hmm, 77 and 91. So for pinion, even after selecting SAE 1045 untreated, we are getting S0 into Y only as 78. whereas for gear it is coming out to be 91. So even after selecting this is coming out to be weaker. Pinion is weaker. Now if you select both the materials as same, if you select both as SAE 1045, this would be further stronger. This value would go up if you change this material to same as this material. So this is already strong. If we are designing it for the pinion, and if pinion can take a load of 30 kilonewtons easily, or the design power of 67.5 kilowatt, gear can definitely take because it is stronger. That is the reason we are taking the pinion, which is a smaller of two with a smaller diameter, less number of teeth, to be made out of a material with larger strength as compared to gear. Is that clear now? Somebody asked me again why we are going for pinion with weaker, stronger material than gear.
Yes, ma'am.
Okay, good. So pinion is weaker, so our design is based on pinion. You might end up with materials such that gear is weaker. ऐसा भी हो सकता है. If you are selecting say cast iron for gear and SA 1045 for pinion, and the number of teeth or Y comes out to be such that S0 into Y for gear is 75 and for pinion is 78. In that case, we'll design it for gear. So this check is must. Which one is weaker? Design for the weaker or for the worst case, so that we are still safe. How long can we continue? Okay, the next is value of FT. Do you have any doubts till then, or so we'll stop here and then we'll continue in the next class, because this is going to take entire next class also. If you have doubt, we can discuss that right now, because this is an important topic. And I'm saying this is important because on the similar lines, we'll be designing the helical gear, the worm and the worm wheel. And for next entire month, probably we'll be discussing only about the gear design. So यहाँ हम जो कर रहे हैं, the same thing we are going to repeat with little modification over there. Do you want me to go for next, or should I explain this part again quickly? Yash, Atharva, Amir, what do you say? Nobody is answering. What do you want me to do? Quick revision. Okay, so the problem is about an electric hoist which can lift a weight of 30 kilonewton at a linear speed of 80 meters per minute. So this is that electric hoist, a simplified representation, lifting a weight of 30 kilonewton at this linear speed. The diameter of this rope drum is given as 600 mm, and this is operated by using an electric motor running at 1440 rpm through spur gears. We have to suggest how many number of stages and what should be the velocity ratio for each stage, and we have to design the gear for continuous duty. This is the problem mentioned. We know that the input shaft rotates at 1440 rpm and the output shaft, from the diameter and the linear velocity, we have seen that the rope rotates at 42.4 rpm, which gives the velocity ratio as almost 34. We know that for a spur gear, the limit of the velocity ratio is 6. So you cannot have more than 6 as the velocity ratio. So we are going for two stage, wherein in the first stage, the velocity ratio is 240 and in the 6. And in the second stage, the velocity ratio is 5.65. So these are the two velocity ratios, and both of them can be used for spur gear. Now we start with the design. So we are designing for the first gear pair P1G1. We have to find out what is the power available at this shaft. So the power at the drum shaft is known. It is lifting a load of 30 kilonewton with a linear speed of 80 meter per minute. So the power required here is 40 kilowatt. And so at the motor, the power required should be little more than that, assuming there are losses of 2% at each gear pair. So this is on an average, the efficiency of a spur gear is 97 to 98%. You can even assume 100% and you can go with the motor rated power as 40. On the safer side, we have assumed the efficiency as 98%. This is for the first gear pair. This is for the second gear pair. Yes?
Why we have taken 0.98 two times?
Yeah, this is for the first gear pair P1G1 and this is for the second gear pair P1G1.
Okay.
यहाँ पर आपका 41.68 kilowatt is the power. There is a loss of 2% here and there is again a loss of 2% here. And so the power available here is only 40.
We have to divide it
Sorry?
We have to divide it as per the number of stages we have
Yes.
calculated.
If you want to find out what is the rated power available for this shaft you divide it only once. So यहाँ पर it will be 40.78 something. And again from here to here it is 41. That means there is a loss of 2% over here, loss of 2% over here. So at every stage we are considering 2% loss and so we are dividing it twice, giving the rated power of the motor as 41.65. Now you will never get a motor of this rating. The motors will be available at 40 kilowatt or 45 or 50 or 60 likewise. So let us pick up or select a motor of 45 kilowatt rated power, but we are again designing based on the service factors. Service condition is continuous duty and light shaft because the input and the output shaft both are having rotary motion. And so the service factor comes out to be 1.5 with a design power of 67.5 kilowatt. So we'll start designing the pinion which is mounted on the motor shaft where the design power is 67.5. So we are selecting the number of teeth as 25 for good balance. We assume the module to be M. So the diameter of the pinion comes out to be 25 m. Peripheral velocity comes out to be 1.88 times m in meter per second. And this is the power which is responsible for transmission of the power or the torque. This is the force and this force is PD, the design power upon Vp, which again comes out to be something like this by M. And next stage is material selection. So we select the material from the design data book such that pinion is stronger than gear from S0 value. But for actual design, we always compare pinion and gear when we multiply this S0 with Lewis form factor Y. Lewis form factor is a term which depends upon number of teeth. So from the formula for 20-degree full depth pressure angle, we have assumed 20-degree full depth pressure angle. So the formula for Y is given from where you calculated YP and YG, and we have to ideally compare which one is weaker and stronger by the product of S0 into Y. So whichever comes out to be lesser of 2, we design for that. So this is precisely the reason that even with S0 196 for gear, since the number of teeth is more, its diameter is more, so we end up with this always stronger than this. So you can actually go for gear with lesser S0 as well. So you can go for cast steel untreated with 140. You can try even if this is 140 multiplied with 0.46, is this still stronger than this or this is weaker? Quickly, someone can tell me. If you go for cast steel untreated, S0 140, what is 140 into 0.46 coming out to be? 64.4. Now then with cast steel untreated, your gear will become weaker. Then we'll have to design for gear. So we'll stop here for the day. Next class we'll continue with the same problem. Is it okay if I engage a class on Saturday? We have a slot on Saturday. So we'll finish this problem. Ananta has taken your attendance. Any more doubts here? Anybody has any doubt? Or we'll stop here. Thank you. Thank you, everyone.